A very good morning to all of you. So this is my next lecture, lecture number 13 on Zener diode, and we are going to see here the characteristics, different characteristics of the Zener diode, how the Zener diode is working, as we have already discussed about how the PN junction is working. So in the same way, we have the Zener diode. In the last lecture, we have seen a little bit about Zener diodes and their symbols and how these Zener diodes are different from PN junctions. So we have this mechanism that is called as breakdown mechanism in the case of the Zener diode. So as we have discussed that there are two type of mechanism in the Zener diode. The first one is the avalanche breakdown mechanism and the second one is the Zener breakdown mechanism. So we have discussed about the characteristic of the Zener diode in the last class also. So in the characteristic, we, as similar to the PN junction, we have to provide some biasing to Zener diode. The Zener diode is basically working in the reverse bias direction or reverse biasing conditions. So in this graph, you can see that the VI characteristic graph, there is some point that is basically VZ, this point. So this negative voltage which comes into picture in the characteristic curve, and this will give you the value of the Zener breakdown region. So this particular region is the Zener breakdown region, and in the same way, that is in the similar way that is in the PN junction, we have a forward bias region. So when you provide forward biasing, this will work in the same way as PN junction, that is when voltage will increase, there will be a change in the current. So after a knee voltage or after a particular threshold voltage, that is around 0.3 to 0.7 volts, there will be a sharp increase in the current. So you can see from the diagram at the top that we have P region and N region as similar to the PN junction. The depletion region is in between the P and N region. So in the Zener diode, we provide negative reverse biasing, that is negative term supply is connected to P region and positive supply is connected to N region. So what will happen? The P region have number of holes and the N region have majority of number of electrons. So the holes will attracted towards the negative polarity and the electrons will attracted towards the positive polarity. In the depletion region, what will occur? Obviously there will be less transition of electrons from N region to P region and from P region to N region holes transition. So in the depletion region, we have deformation of electron and hole pairs, or you can say that the breakdown mechanism will occur between electron and hole pairs. In the PN junction forward biasing, we have the recombination of electron and hole pair. So what are the two phenomena are? First one is the recombination phenomena, and the second one is the generation phenomena. So there are two phenomena basically on which all the semiconductor devices will work: the regeneration phenomena and the recombination phenomena and the generation phenomena. So in the recombination phenomena, what will happen? There will be a forward biasing and there will be a recombination of electrons and hole pairs in the depletion region, and that's why the depletion region is very narrower as compared to the in the case of the reverse biasing. So basically, recombination occurs in forward biasing condition, that is forward biasing, and generation of electron and hole pairs will occur in reverse biasing. So if you remember these two phenomena, you can grasp over the whole thing that on which phenomena the Zener diode is working in the reverse bias condition and on which phenomena the PN junction or the Zener diode is working in the forward biasing condition. So basically in the last lecture, we have seen that lasers, LEDs and all these type of semiconductor which gives you light will works on the phenomena of recombination of electron and hole pair. So whenever there will be recombination of electron and hole pair, there will be emission of light or emission of photon. So in the recombination process, there is emission of photon. In the generation process, there is emission of electron and hole pairs. So they will create new electron and hole pairs which will generate electrical energy. So in the depletion region, what we have drawn here, that is the splitting of the electron and hole pair or the generation of electron and hole pair which is already combined in the recombination process. In the next picture, what we have drawn, that the Zener breakdown region, the N region and the P region, in the same way we are applying the reverse conditions, like the negative region is connected to the positive polarity and the P region is connected to the negative polarity. So in the same way, we have a depletion layer created in between the P and N region, and there will be a potential difference will be created across the junction, which is called as built-in potential. So we have discussed built-in potential, that is VBI, which is built-in potential. So there will be some value of built-in potential across the depletion layer, so that the N number of electrons, whatever is left in the N region, because these electrons get attracted towards the positive polarity, so whatever the electrons remains in the N region will cross the junction. Similarly, whatever the holes remains in the P region will cross the junction. So there will be some potential barrier between these two regions. So next, what basically breakdown mechanism is. So in avalanche breakdown or in Zener breakdown, there are some differences between these two mechanisms. So in avalanche breakdown mechanism, the electrons are excited in the reverse bias mode. Both conduct in the reverse bias mode. Either it will be a avalanche diode or a Zener breakdown mechanism. But the start of knocking off the free electron in the valence band, and hence the current rises abruptly in the case of the avalanche breakdown as in the case of the Zener breakdown. Also, there are various applications, industrial applications, where avalanche breakdown will give you better result because it has a multiplication factor, or it has a gain factor. So here there is a gain, there is no gain. So here gain mechanism is there in the case of the avalanche, but in the case of the Zener there is no gain mechanism. Why there is gain mechanism? Because there is a sudden multiplication of the electrons, hence it is called as avalanche breakdown mechanism. So there will be one electron is created, one electron hole pair is created, it will hit another electron hole pair, and it will create another electron hole pair. So that's why there will be a chain process of creation of electrons, more and more number of electrons in the case of the avalanche breakdown. So in the case of the avalanche breakdown mechanism, there is much creation of electron and hole pair, but in the case of the Zener breakdown mechanism, there is creation of electron hole pair, but not like a gain mechanism will be followed in the case of the Zener diode. So this is the basic difference between avalanche and the Zener breakdown. So next we have differences. We have listed here differences between avalanche and breakdown, which are some major differences. So the first one occurs in heavily doped diodes, basically Zener diodes. It basically occurs in heavily doped diodes, and the avalanche is basically in lightly doped diodes. Ionization takes place by electric field here. So here there is a ionization takes place. Obviously, ionization means the number of electrons holes pair created through any process of ionization. So here ionization takes place due to electric field, and it occurs even with less than 5 volt. So even you apply the 5 volt to the Zener diode, they will work, or there will be ionization taking place, and there will be formation of new electron hole pair. After the breakdown, voltage across the Zener diode is basically constant. So a particular, because we have seen in the characteristic curve that after some time it is constant. So after a particular Zener voltage, it is constant, but in the avalanche, the voltage duration, you can say, the voltage value is much higher as compared to the Zener diode. So we have some listed some differences between avalanche and Zener, and in the case of the avalanche, what will occur? In the case of the avalanche, it occurs in lightly doped diodes. Ionization takes place by collision of electrons and hole pairs. So that's why I have told you that it has some gain mechanism. So whenever one electron hit another electron hole pair, it will create new electron hole pair. So it occurs at higher voltages, as we have seen that the characteristic of the Zener is something like this, and for the avalanche it is like this. So the VI characteristics, if we talk about VI characteristics, so sorry, this is V and this is I, VI characteristic. So for VI characteristic, the Zener breakdown will occur earlier as compared to the avalanche breakdown. So after breakdown, voltage across the PN junction is it is not constant at all. That in the case of the Zener diode, it is almost constant after the breakdown voltage, but in the case of the avalanche, it is not constant, it is varying. So next we can see from the graph also that how the breakdown will occur in the reverse bias direction. In the forward bias, it is same, that as you increase the V value, current will increase in the forward bias condition. So we can see that the graph is exponentially increasing. So it is exponentially increasing graph in the case of the forward biased. But in the case of the reversed biased, what will happen? There will be a Zener breakdown voltage and there will be a avalanche breakdown voltage. So here avalanche breakdown voltage VA is always greater than VZ. So in the case of the reverse breakdown or reverse biasing, we have Zener breakdown and two mechanism, that is Zener and avalanche, and we have in the Zener voltage breakdown is occurring earlier as compared to the avalanche breakdown. So we can plot these graphs in our labs also. We can take values of the V and I characteristic, V and I values, and we can draw these characteristic curves in the labs by implementing the circuit in the breadboard. So next we have the symbol. We have already discussed that Zener diode is a diode which operates at a specific voltage in reverse mode of operation. So this is the major point, that it works only in reverse mode of the operation. It is the only diode which operates in reverse bias. It will only turn on at a specific voltage, and for rest voltage it will remain off. So until unless you reach a particular point, that is a breakdown voltage or a Zener breakdown voltage, only then the current will abruptly increases or sharply increases. Before that the current is almost zero. So the symbol of the Zener diode is same as the PN junction diode. There is a Z type of symbol in the cathode side and the anode side is similar to the PN junction. So this is your positive terminal, this is your negative terminal. So these type of Zener diodes are basically used in various applications where we want to make it like Zener as a voltage regulator. You can implement some voltage regulations techniques using Zener diodes. So Zener diodes can be implemented in various ways. So we can use PN junction diode. On the other hand, we can also use Zener diode. So as a voltage regulator, it has a major advantage. So main application of the Zener diode we will discuss later is as a voltage regulator. So next we have discussed already built-in potential, which is VBI. For both the cases, for it will be for PN junction or maybe for Zener diode. For the forward biasing condition, VBI is equivalent to KT by E ln ND NA upon NI square. So here KT by E is equivalent to 0.0259 electron volt. ND is basically donor concentration and Na is basically acceptor concentration. So by this formula we can calculate for both, either it will be a PN junction or for Zener diode in the case of the forward biasing. So next, how the Zener diode is constructed. So construction of Zener diode is just like an ordinary diode, except that it is having high doping. So we have to make high doping as compared to the ordinary diode. In the PN junction, we doesn't require a heavily doped thing. So we can dope with PN junction diode with a pentavalent type of impurity, and we can create our Zener diode. So more impurities are added to achieve better current performance. So whenever you increase the doping concentration, either Na or Nd, you will just get your much higher current performances. So in the construction point of view, we have P layer and N layer. In the same way, that is P layer is constructed with your trivalent impurities What are trivalent impurities? Like boron, aluminium. These are trivalent impurities, etc. And the N layer is constructed with pentavalent impurities. And what are these impurities? Like arsenic, antimony, or your phosphorus. So these type of impurities can be used for creating your P layer and the N layer of the Zener diode. So whenever you implant trivalent impurities, it will create acceptor type of impurity, and there will be more number of holes will be created. So that's why it will create your P layer. Similarly, when you implant pentavalent impurities, it will create more number of electrons. So in P layer, we have more number of holes, or this is due to trivalent impurities. And in N layer, we have more number of electrons, and it is due to pentavalent impurities. So by this way we can create, as in the case of the PN junction, we have created the P layer and the N layer. In the same way we create for the Zener diode the P layer and the N layer. Only the thing is we have to highly dope P layer and N layer. Whatever the impurities you are adding, that to be in high amount. So this particular portion is your depletion layer. And this depletion layer has some potential barrier to cross the electrons from N layer to P layer, and the holes, whatever the rest holes is left from the P layer to N layer. So this is your potential barrier is required. So here we have a negative polarity, and here it has a positive polarity. So how the working of the Zener diode is there? So when the junction is reverse biased, then the diode starts conducting at a specific voltage, and as the reverse bias voltage exceeds the desired value, the junction breaks down and diode starts conducting. So in the same way as in the PN junction, in the reverse bias condition, there will be a no breakdown mechanism in the case of the PN junction. Here the breakdown is there. So whenever the junction is reverse biased, when you provide P type with negative polarity and N type with positive polarity, so there will be a reversed condition. And in the reversed condition, whenever you increase the voltage and it exceeds a desired value, the junction breaks down and the diode starts conducting in a proper way or abruptly, as we have seen in the characteristic curve, that it's like this. In the forward biased mode, the Zener diode operates like an ordinary diode, but it is always used in reverse bias mode in various applications, as I have discussed. That these applications are as a voltage regulator you can use, or somewhere in industrial applications wherever we required as a reverse bias condition, like for example for photodetectors. For photodetectors we can use our Zener diodes or a particular type of diode like pin or avalanche diodes. So whenever the light falls on the photodetectors, the electron hole pairs get generated, and these will give you the electrical current in the circuit. So this is the working of the Zener diode. Next, the characteristics of the Zener diode. In Zener diode, initially the current is very less. So there are some major points. Current in Zener diode as compared to PN junction. Is very less. So in Zener diode, initially the current is very less in reverse bias mode, and slowly as the junction breaks down, then the current starts rising abruptly and the diode starts conducting. So whenever there will be some junction breakdown, only in that condition the diode will starts conducting. So this region, this is your Zener breakdown voltage, and you can see that the current starts increasing sharply. Here 0.7 volts in the forward biased is taken for silicon. So if we take silicon type of Zener diode, it has a 0.7 volt built-in potential. So it is built-in potential or knee voltage, you can say. Similarly, for the shaded region is shown here, that is the reverse breakdown region. So the shaded region is basically the reverse breakdown region, and here the diode conducts abruptly in this case. So in a Zener diode is much like a normal diode. The exception being is that it is placed in the circuit in reverse bias and it operates in reverse breakdown. So this typical characteristic curve illustrates the operating range for a Zener breakdown. So the range of the operation in the case of the Zener diode as compared to normal diode is much higher, as you can see. But if you see about avalanche diode, so in the case of the avalanche, we have much higher range. As compared to Zener. Because why? Because the avalanche breakdown occurs after the Zener breakdown will occur. So there will be a much higher voltage as compared to the Zener diodes. So there are numerous applications of the Zener diode. As I have told you that Zener diode as a voltage regulator. So this circuit shows Zener diode circuit as a voltage regulator. Here we have placed a Zener diode, that is a positive terminal and a negative terminal. A resistance values is there. So this is your resistance R, and we apply a voltage source, that is U input or V input or V out, the output voltage. So from here we will take V out. So the Zener diode is used as a voltage regulator widely to protect electrical appliances. Here in the circuit we can see that Zener diode will start conducting at a specific voltage, and then only we will get the output. Else what will happen? Else for all other voltage there will be a no output. So for different appliances we have to see that the voltage level is not too much exceeded, so that it will harm your appliances. So as a voltage regulator we can use the Zener diode. So and then only we will get the output. Else for all other voltages there will be a no output, and hence the appliances will be safe from high voltage fluctuations. So whenever there will be fluctuations in the voltage, so the major thing is voltage fluctuations. So if there is voltage fluctuation, your appliances get disturbed or appliances get, applications are like as a voltage regulator. So to protect our appliances from harm, we use this type of Zener diode circuit. So up to this point what we have covered, that how the Zener diode is working, how the Zener diode is different from a normal diode. PN junction diode is obviously the best diode we can use for different multiple applications. So but whenever we require some voltage regulation, whenever we require some circuitry like we require a reverse biasing condition, that the light will fall on the circuit and the electron hole pair gets generated, and we require some light, like in the case of the lasers or LED, we require some other phenomena. So in the case of the laser and LED we require the forward biasing phenomena, but in the case of the detectors we require reverse biasing. So by this way we can see that there are numerous applications of the Zener diode, and we will see in the next lectures how the things are going to be in the case of the MOSFET and FET, how the Zener diode it can help also there. So what are the advantages and disadvantages of the Zener diode? So these are some advantages which we already covered, that it protects appliances, easy in construction, less cost, and it has a small size as compared to the PN junction. The size of the PN junction and the Zener diode is similar almost. You have to see that there is some differences. So it protects appliances easy. It is easy to construct. We have a very less complex circuitry here. We have to only fix a resistance, a Zener diode, and we have to input some voltage and take the output voltage, so that we can use that voltage as a voltage regulator. So what are the disadvantages? Diode gets heated up when reverse bias voltage exceeds a desired value. So whenever we require some voltage level, we have to increase the voltage particular to a particular Zener breakdown voltage, which is Zener breakdown voltage, and after that voltage level only there will be a work starts, Zener starts conducting. So these are two major advantages and disadvantages of the Zener diodes. So in the next we have Schottky diode. This is some little bit information about Schottky barrier diode. So what is Schottky diode? Schottky diode is named after a German physicist, which is Walter H. Schottky, and it is also known as hot carrier diode. So another name for Schottky diode is hot carrier diode. It is another form of the diode. So it is a semiconductor diode with a low forward voltage drop and a very fast switching action. So it will switch from reverse bias to forward bias to reverse bias very fastly. So when current flows through a diode, there is a small voltage drop across the diode terminals. A normal silicon diode has a voltage around 0.6 to 1.7 volts, while a Schottky diode voltage drop is approximately between 0.15 to 0.45 volts. So this lower voltage drop can provide higher switching speed and better system efficiency. So this type of diode can be used in multiple applications where we require higher switching speeds and better system efficiency as compared to the PN junction diode and the Schottky Zener diodes. So we'll later on see about how the Schottky diodes can be useful in making these type of devices where we require higher switching speeds and high system efficiency. So till now what we have covered about the PN junction, the Zener diodes and the Schottky diodes, which is also a popular diode in which we have only less knee voltage. So if it has a less knee voltage, so what will occur that in the forward biased, this is your VK. For the normal PN junction, it is for silicon, it's 0.7. This is for normal, but for Schottky, for silicon, it is around 0.15 to 0.45. So it is around 0.25. So there is a major difference between the normal PN junction and Schottky diode silicon structure. So the knee voltage is lesser as compared to the normal PN junction. So whenever you provide a smaller voltage, the current will rise sharply. So there will be a more switching action will taken place in the case of the Schottky diode, and the speed is also very fast. So here the speed is fast as compared Zener or normal diode, and the obviously knee voltage VK is less as compared to normal diode. So this type of Schottky barrier diode and Zener diode, these are a special type of diodes, and we can use these diodes in multiple applications. So till now, whatever we covered about the diode, their characteristic, the characteristic for the Schottky diode is similar as compared to the Zener diode. Only the thing is, it will have a knee voltage which is very less as compared to the normal diode. So thank you so much. In the next lecture, what we are going to see about the MOSFETs, the FETs and depletion type of MOSFET and the enhancement type of MOSFET, their construction and their working, and then their applications as compared to the diodes which we have seen. So somewhere these diodes are used in various applications, and Wherever we require the FETs and the MOSFET, there we use the FETs and the MOSFET for different semiconductor devices.